The first section of the data fitting unit is polynomial interpolation. Here we want to find a model so that the data points lie right on the graph of the model. We want an exact fit here. The example shows a table of values, and these happen to be areas under the standard normal curve to the left of different values of z. To find the area that corresponds to z equals 0.92, which is not on the table, we'll use the interpolant to estimate this area. So this is a typical application of polynomial interpolation. We have accurate data in a table, but we want to find a value that's not in the table. So I'm going to use two different interpolants here and compare the result. The first one is a linear interpolant, and that is a model that looks like this: c1 plus c2x equals y. We're changing our notation from mx plus b to this. Our coefficients c1 and c2 are what we have to find. They are still the y-intercept and the slope, but we're using this notation and the method that will generalize to higher degree polynomials. So for the linear interpolant, I need two data points, and I'm going to choose these, the 0.75 and 1, that is data point with the z value just below and just above the 0.92, which is what I'm trying to find. So if these data points lie on the graph of the model, it means that they satisfy the equation. When I use the value of 0.75, I substitute it in there for x, I should end up with 0.7734, the table value. And likewise for the second data point, when I substitute 1 for x, I should end up with 0.8413 for y. And that is the system of equations that I will solve to find c1 and c2, the coefficients of the interpolant. I can solve this system using Gaussian elimination, that would be one method, or using a matrix equation. And that's going to be the method that I want to use here, matrix equation. I have the matrix of coefficients, 1c1, 0.75 c2. c1, c2 are my unknowns, and the constants to the right of the equal sign there in my system are 0.7734 and 0.8413. The second row here is 1c1 and 1c2. So there's my matrix equation. I'm going to give these matrices names. This one is going to be V. That stands for the Vandermonde matrix, and we talked about that a little bit. We'll look at some properties of that in just a minute. This is the unknowns here, coefficients, so I'm going to put that in a matrix called C. And the constants over here on the right are just my y values. So I have this matrix equation right here. And the solution to that matrix equation is inverse of V times y. Notice the matrix V is square and it's invertible. It's invertible because the determinant is not 0. It's 1 times 1 minus 1 times 0.75. So we know V has an inverse here. And so I'll find a unique solution. It would be easy enough on paper to find the inverse of V and to multiply that by y, but I'm going to go ahead and use Matlab. So I'll type in the matrix V, 1, 0.75, and 1, 1. And I'll type in the matrix Y. That's the column of constants there. And that is 0.7734 and 8413. And that's all I need for my calculation. I'm going to pack these coefficients into a matrix called C, inverse of V times Y. And this is why I like this method here rather than the Gaussian elimination, because now when I make my estimates, I've got those coefficients packed right into a matrix called C. C of 1 is the y-intercept. C of 2 is the slope. So for my estimate of 0.92, I'm going to take C of 1 plus C of 2 times 0.92, 0.8196. There's my first estimate for the area under the standard normal curve to the left of 0.92. Okay, so my estimate here is going to be 0.8196, and that's from the linear interpolant. Now, how accurate is that estimate? And is this linear interpolant the best choice to find my estimate? If we look at this scatter plot of all of the table values, I notice that I get a curved pattern and not a straight line. So maybe a better interpolant would be a quadratic or cubic or quartic, just some other polynomial that has a curved pattern. This time I'm going to find a cubic interpolant. And how's that going to look? I have C1 plus C2x plus C3x squared plus C4x cubed equals y. I need to find 4 coefficients here, and so I'll need to use 4 data points. I'll choose 2 above and 2 below from my table. So the data points are going to be 0.5, 0.75, those are the 2 below, and 1 and 1.25. So the 0.92 will squeeze right in between those two. For 0.5 I have 6915 from the table, 0.7734 from the table, 0.8413 and 0.8933. If they are to lie right on the graph of the model, it means they're going to satisfy that equation. So I'll build a system of equations by substituting each data point into that model. Again, we're going to use a matrix equation to solve this system. And I'm going to call it V times C equals Y. The matrix V is going to be the matrix of coefficients from the system that I get when I substitute each of these data points into the model. So my first equation, I'm going to have 1 times C1, x times C2, x squared times C3, and x cubed times C4. The second data point, when I substitute that in there, is going to be 1 C1, 0.75 C2, the square, and the cube for the coefficients of C3 and C4. I'll substitute 1 in there, and there I have 1 squared, 1 cubed. You can see how this is going to be put together quickly. It comes from a system of equations. And of course C is going to contain 4 values, 4 unknowns, and the equal sign here, I can't squeeze y in there, but y is going to be the values that I end up with when I substitute those values of x, and these are my table values for y, going right down the column. Let's take a look at how the Vandermonde matrix gets put together here, or the properties of this Vandermonde matrix. First of all, it's square. It's square because I have a column for each coefficient that I'm trying to find. Notice back in my model right here, I have 4 coefficients, and each one of those coefficients corresponds to a column. So the number of columns here is 4. 4 columns. And I have 4 data points. Each one of them gives me an equation in my system. So each one gives me a row. It's going to be 4 rows. And those two things match up to make V square. Okay, the first column, column 1, of course, is all 1s. And that's because every time I substitute a value of x into this model, the first coefficient, C1, has a coefficient of 1. So the first column is 1. The second column, column 2, are my x values, right down the column. And then, of course, the third column is the square of my x values, and the fourth column is the cube of my x values, and that's the Vandermonde matrix. It's square, it's invertible, and the solution to my matrix equation, once again, is C equals V inverse times y. So I'm going to go into Matlab and type in V, type in y, and get my 4 coefficients. So in Matlab I typed V, the Vandermonde matrix, and I type the y values in a column there. And once again I'm going to take my solution and call it C. These are the coefficients that I'm going to find for my model. Inverse of V times y. And there they are, 4 coefficients. Now to calculate the estimate of the area corresponding to z of 0.92, I'm going to type that cubic polynomial in here. C of 1, that's my first coefficient, plus C of 2 times 0.92 plus C of 3, that's going to be times 0.92 squared, plus C of 4 times 0.92 cubed. And I'll get the estimate 0.8211. Well, let's compare this with the estimate that we got from the linear interpolant. So let me scroll back here. With the linear interpolant, I got 0.8196, and with the cubic, I just found 0.8211. So they are quite different, and which one's more accurate? Well, we could look this up, the actual value, look up on a website or use your calculator and actually find a good estimate from another table source for the z value of 0.92. And when I do that, I found, so we're going to compare both of these with the value 0.8212. That would be the most accurate. And you can see that using the cubic interpolant, the estimate comes really close.